Good morning students, welcome to Design Laboratory. So in the last video, we seen how to conduct the experiment on longitudinal vibration of helical spring. So in the experiment, we made some observations. The length of spring is 215 mm, mean diameter of spring is 33 mm, and wire diameter is 1.5 mm. So now in the observation table, we noted down the weights. So we have taken three different loads. 0.5 kg, 1 kg and 1.5 kg, and we have considered number of oscillations as 10. Then we have calculated or we have noted down the time for 10 number of oscillations for different weights. After that, measured the deflection also, that is initial length of spring was 215 mm. After attaching the mass as 0.5 kg, that time what is the length we need to measure, then you have to take the difference to get this deflection value. So after that, this P you need to calculate by using P by N, and K is W by delta, and K mean you have to calculate. So these two here you need to note down from the conduction of the experiment. After that, it is a calculation part. So here first one is experimental time period. So T experimental is given by P by N. So the first reading is 5.72 seconds divided by N is number of oscillations as 10. So it is 0.572 second. Then similarly for the remaining time period you need to calculate the experimental time period. Then stiffness of the spring, that is K1 equal to W by delta. So here W is 0.5 kg divided by delta means deflection is 0.042. Substitute that, you will get the K1 as 11.9 kg per meter. Similarly, for a different deflection and a different load, you need to calculate the remaining two values of the K, that is K2 and K3. Then you need to calculate mean stiffness. So it is given by K1 plus K2 plus K3 divided by 3. So you will get K mean as 11.907 kg per meter. Then need to calculate theoretical time period. So P theoretical is given by 2 pi into square root of W1 divided by K mean into G. So W1 is 0.5, K mean is 11.907 into G is 9.81. To substitute and simplify that one, theoretical time period will be 0.4123 seconds. Similarly, you have to carry out the same procedure by substituting the values of W2 and W3 to get the value of T2 and T3. Then the fifth one is theoretical frequency, that is F theoretical you need to calculate. So it is given by 1 divided by T theoretical. So since we are having three different time period, theoretical time period, so you need to calculate three set of theoretical frequency, that is given by 1 divided by T theoretical. To substitute that, you will get 2.425 cycles per second. Similarly, for the second time period and third time period, you need to calculate the frequency. Then the sixth one is experimental frequency you need to calculate. So it is given by experimental is given by 1 divided by T experimental. So this time period is whatever the time period you have noted down from the conduction of the experiment, that value you have to take here. So it is 1 divided by 0.572 is equal to 1.74 cycles per second. Similarly for the remaining two set of readings. Then you need to calculate the natural frequency. So the theoretical natural frequency is given by 2 pi by TTH1, that is theoretical time period. To substitute that, you will get it as 15.23 radian per second. Likewise, you are having T2 and T3. So with the help of those values, you can get omega T2 and omega TH3. Similarly, for the experimental natural frequency, 2 pi divided by T experiment. So we are having three set of experimental time period. Substitute that, you will get the natural frequency for the experimental values. So if you have any doubt, you can leave a comment in the comment box. Thank you.